Okay, so here's how this problem works. So we're starting with the free response questions here, and you start with this question. So, um, okay, it says, so for parts of the free response question that require calculations, clearly show the method used and the steps involved in arriving at your answers. You must show work to earn credit for your answer. Um, what's this? To receive credit for your answer, examples and equations may be included in your answers where appropriate. Okay, so we have this graph, right? And it starts at 24.8 and it ends at 22.2. And that happens over some time that's not labeled or not demarcated, so we don't know exactly how much time. So a student added a sample of ammonium nitrate to water and measured the temperature over time. The data are shown in the graph above. What is the value of delta T that the student should use to calculate Q? Okay, A. And B, according to the graph, is the dissolution of ammonium nitrate endothermic or exothermic? Explain. All right, so A and B can be done pretty readily, straightforward, like right away from looking at this, from what we've studied. Part C can too, but it might require some more discussion. So we're going to start with A and B, and then we're going to move to C. And C says, asks, are the strengths of the interactions, and it really should say among the particles in the solute and among the particles in the solvent, because between refers to just two things, right? So like there could be strength between, of interaction between two particles, but we're really talking about a lot of particles here. So these are both ensembles. So among particles is more appropriate. Between two things, among more than two things. So among the particles in the solvent before the solute and solvent are combined, greater than, less than, or equal to the strengths of the interactions among solute particles and solvent particles after dissolution. Explain. Okay, that's a really good question, and we'll talk about it. But first, we're going to talk about A and B. So, gentlemen, you've had time to look at A and B. Antonio, what'd you get for A?
For A, I got 2.6.
2.6. Okay, so if you do 24.8 minus 22.2, you get 2.6. Yeah, that makes sense to me. Kaiten, did you get the same thing?
Yeah, I got the same thing.
Perfect. Okay, and then according to the graph, is the dissolution of ammonium nitrate endothermic or exothermic?
Endothermic.
Endothermic. Why? How do you know?
Because as time goes, the temperature drops, which means it's absorbing energy.
Right. The dissolution process itself is absorbing heat from the water. Exactly. Okay. So we can tell that this process is endothermic. Very good. So are the strengths of the interactions among the particles in the solute and among the particles in the solvent before the solute and solvent are combined greater than, less than, or equal to the strengths of the interactions among solute particles and solvent particles after dissolution? Okay, so have we thought about this problem or this question, or are we still thinking about it?
I thought about it.
You've thought about it. Okay, do we need more time to think about it, or do we want to just kind of give an answer right now?
I'm okay with going with the answer right now.
Yeah.
Okay. So what would you say, Antonio?
I would say they're weaker.
They're weaker before or weaker after?
After.
Weaker after. Okay. And what would you say, Kaiten?
Well, this is the thing, is that I can come up with reasons for all three in my head. I just don't know which, if any, are correct.
Okay. Antonio, why did you say that the strengths of the interactions when the particles were separated, right? When we had ammonium nitrate solid and when we had water, pure water liquid, why were the interactions stronger then than they were after the dissolution?
Well, it's got something with the interaction with the water. I mean, they pretty much broke apart, right?
Yeah, okay. You're really getting there, right? So like, let me just open up my drawing. Okay, so think about this process, right? So this is endothermic. Okay, and we figured that out, right? So endothermic implies that delta H is greater than 0, okay? So if you think about that in terms of bond enthalpies, okay? If you think about bond enthalpies, and in this case, that's basically what we're dealing with. We're dealing with bond enthalpies in the case of ammonium nitrate, and we're dealing with hydrogen bonds in the case of water, okay? So think about this as a bond enthalpy situation, right? So if you think about it in terms of bond enthalpies, then what that gives you is reactants minus products is greater than 0, okay, because delta H is greater than 0. So that means that you have greater bond enthalpies here. And then lesser bond enthalpies. Okay, lesser bond enthalpies. And what that does tell you is that the strengths between or among the particles in the solute and solvent, okay, these are greater before. So greater interaction strength before dissolution. And the thing we won't get to is why that would even happen. So that happens because of the Gibbs free energy. So it turns out that the delta H is positive minus T delta S. Yeah, it turns out that the increase in entropy can overcome a decrease in enthalpy. So this can still be a spontaneous process, okay? This process can still be spontaneous because the amount of disorder, which is, that's in, and I gotta be honest with you, like that's a hard concept for me to think about, like that disorder is an energetic effect. I still like struggle with that just intuitively, like understanding how and why the universe would want, you know, greater disorder. I feel like there's got to be some like more direct physical explanation behind that I just don't understand. And the thing that we use in chemistry is number of microstates, but I still don't feel like that's a real physical factor. So I still struggle to understand like what's going on exactly with enthalpy. Or sorry, with entropy in cases like this. In other cases, it makes sense to me, but like in this case, it's like really, really hard for me. But regardless, so what we generally say in chemistry is that because we're introducing disorder and because the universe wants to
dissipate.
Yeah, but like sort of verge toward increasing amounts of disorder, right? Because the universe tends to get increasingly disordered, then that's what's overcoming the energetic cost of breaking or disrupting these initial interactions, which are stronger than the interactions among dissolved species. Okay, that's the deal. But I don't think we're going to get there in the book because I think the AP curriculum's been truncated for this year. Okay.
Okay.
Which is a shame. All right, so I'm going to ask. I'm going to pause the. Well, first off, what are our questions? Okay, and is this written well enough? Can we understand and follow the explanation that's written on the board, or should I rewrite it? Up to you. And then, what are our questions at this point?
Yeah, so I can follow this. So basically, what you're saying is that so since the bonds at the end are less energetic, then they're weaker?
Yeah. So since the bonds at the end have less energy required for breaking, right? Like so they are weaker. That's right. It takes less energy to break them. Yes, and they are weaker. Yes. Mm-hmm.
Okay, and that's a result of them having absorbed energy from the surroundings.
Release, right?
Sure. Yeah. It's a result of their intrinsic like electronic nature, but they were formed by the absorption of energy. Like absorption of energy was required to get to those bonds from the original bonds.
Right.
Yeah.
Okay.
Yeah, and you can tell, like that's a piece of evidence that tells us, right, that those bonds are weaker. Does that work, Keaton?
Yeah.
Okay, cool. Antonio, any questions?
Now I can follow it.
Okay, then I'm going to get us on to the next question. So that was a really good job, gentlemen. Okay. Okay. So, hey, Symphony, how are you doing? Welcome, Symphony. So, Symphony, we just went through the first problem. The full discussion of that will be up on YouTube later today. And then now we're going through question 2. So, for parts, we're looking at the free response questions. So for parts of the free response question that require calculations, okay, same instructions as before. So really important to show all of your work, otherwise you won't get any credit. So, okay, methane gas reacts with fluorine gas to produce fluoromethane and hydrogen fluoride. A particulate representation of F2 gas is shown above its formula in the equation below. Using the key provided, draw particulate representations of CH4 gas and the 2 product molecules of the reaction above their formulas in the equation. Okay, so it kind of shows you what you're dealing with there. So we're just drawing these little things out. And then use bond enthalpies to calculate the numerical estimate for delta H. Okay, and then what are we going to do last? Here's the energy of the reactants on the right side. And you're basically going to draw a reaction diagram that corresponds to the value of delta H for the reaction. Okay. Vertical headed arrow. Yeah. So okay, we probably haven't seen this before. So like, we'll talk about part C, but I want you to go ahead and do part A and part B, okay? We can do parts A and B with what we already know pretty straightforwardly. Part C is just a different format than we're used to, so we'll talk about that in a second, okay? So parts A and B, let's go ahead and take, let's take 5 minutes, okay? Hey Siri, set timer for 5 minutes.
Okay, 5 minutes and counting.
Okay, I don't think any of us should have had a difficult time with this one. So this one should have been pretty straightforward. Like if this is C, right, you draw your little C and then you make sure it's like shaded in. And then if this is H, you draw H, 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 and then there's your F2, and then you should get C, right, with H, 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 and then one little F there. And then you should get another F with another little H, right? Okay, and then that's what it should look like. So did everybody get that, or do we have some questions about what's going on there?
No, I got that.
Okay, cool. So Antonio, Symphony, all good on that one?
Yeah.
Okay, I'm gonna erase that drawing then. And then next order of business. Okay, so I did this last one a little differently than I normally would have. So you can do reactants minus products. That's the standard way to do it. So you go like reactants minus products equals delta H when you're dealing with bond enthalpies, right? So delta H of bond enthalpies. Okay, I'm gonna put a little B there for bond enthalpy. I know that's not formal notation, and you know my my chemistry professor friends might want to scream at me for doing that, but I think it's okay. So when you're doing that, right, what you get is what's going to change, right? One CH bond is going to break. So you have on the reactant side, you've got 413, right? Plus you've also got on the reactant side an FF bond, 155. Okay, and you're going to subtract, right? One CF bond is going to form and one HF bond is going to form. Those are the things that are changing. So 485 plus 567. Okay, and when you do that, you should get negative 484 kilojoules. Is that what you guys got? Did I do that math right?
Yeah, that's what I got.
Okay.
Good.
Okay, so I'm going to leave it like that for now. Let's just leave it like that. I feel like that's pretty good. Is that how you did it, or was there a different way? Did anybody do anything like significantly differently than I did?
No, that is exactly what I did.
Okay, let's just call it there. Let's just call it there then. Okay, that's good enough. Okay, okay, so then, okay, so I'll actually show you how I did this in my head super quickly, but this only worked because like we had exactly what we needed and there was one breaking and one forming each time. So like I knew that this CH was going to turn into a CF. So I just did the subtraction right here and I got -72. And then I knew that this FF was going to turn into this HF. So I did the subtraction here and I got -412. And then I just added them to get -484. Sorry, I couldn't help myself. So that's just a little shortcut that I was able to do. So I don't know if that helps you or not. I recommend just using the standard method that I showed you, but this could be a cool little way to check yourself. Okay, and it's also another like little way to think about it because maybe you think about it that way and you say to yourself, hey, you know what, this stuff isn't so complicated. Okay, so there we go. For some reason, that just felt a little more approachable to me. Okay, so the energy of the reactants is shown in the following energy diagram. On the right side, draw a horizontal line segment to indicate the energy of the products. Draw a vertical double-headed arrow on the graph that corresponds to the value of delta H for the reaction. Okay, so basically in this case, right, you're going to draw a little arrow. Like I'm just going to show you what it's telling you to do because if you're not used to seeing this, you're not used to seeing this. So this is what you draw, right? And then if this is the delta, this is the so energy. What they really mean is enthalpy, right? I don't know why they're using energy. That's a little crappy because they don't actually give you Gibbs free energy. What they should be, I mean, I guess they could call it internal energy U, but they really ought to just be using H enthalpy. Like that's the better quantity to use in this case. So I would use H enthalpy. And if C4F2 is right there, okay, then where is where are we going to put the products? Okay, so CH3F and HF, where are they going to be? Are they going to be up here relative to the reactants, or are they going to be down here, or are they going to be even up with the reactants? Where are they going to be? Okay, so what do you think, Symphony? Where would they be?
I'm not sure.
You're not sure. Okay, and then what do you think, Antonio?
Think above.
You think above. And Caton, what do you think?
It's going to be below.
Why do you think below?
So because delta H is negative here, it's giving off that
Asia?
energy.
Because delta H is negative, what's happening?
It's giving off that energy. So that means that the internal
heat's
energy
being released, right? Heat's being released. Okay. So heat's being released by this reaction. Absolutely. Okay. So it's going to be below somewhere. And we can leave it there. I'm just going to draw it a little more neatly. So right there. And this is where you'd have your CH3F plus HF, right? And then your double-headed arrow would be like this, okay? So like dot, 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 like that. And that would correspond to -484 kilojoules, okay? That's what you would have there. Okay, does that make sense, scholars?
Yeah.
Okay, we're just not used to seeing that. We could have been doing this the whole time, okay? In fact, next year I probably will now that I've seen this thing. So we could have been doing this. This is a simple thing to do. It's nothing you don't understand, okay? So that's how we do this. All right, so I feel like that's a good stopping point for this bit, unless anybody has any questions about these free response questions.
I'm good.
Okay.
No, I'm good.
Okay, I'm gonna double check if there's nothing else. No, there's nothing else. Okay, so I'll go ahead and pause this. Actually, I'll pause the recording. Okay, so I'm gonna share this slideshow with you from Dr. Zhu, and this is about the AP exams. All right. Okay, so new format. We can all take a 45-minute online exam with free response questions at home. The College Board will use their testing platform to prevent cheating. Good luck. The content on the exam, good good luck to the College Board. I know we won't cheat. Okay, we will be honest and we will do things the right way. In general, content covered by the beginning of March will be on the exam. So there's a content specific little piece that we're going to look at in a little bit. College credit, you'll still get your college credit, okay, with the modified format. And there are some resources for the daily AP course schedule and then the AP YouTube channel. Okay, great, good stuff there. And then here's an important date, April 3rd. So April 3rd, the full AP exam schedule, specific free response question types that will be on each AP exam, and additional testing information will be released. So it looks like we might not even be doing multiple choice for this. Okay, so we've got to wait until April 3rd to really know all the details. But let me see if I can get this other content specifics thing. Okay, there we go. So.
Wait, so Dr. J, do we not know the day, or is it still going to be on May 7th, or is it, or we don't know
No,
yet?
we don't know the date yet.
Okay.
We don't know the date yet. It doesn't look like, it looks like it's going to be, this is tough. So, okay, course specific exam information, chemistry, units 1 through 7. Yeah, exactly what I thought. Okay, so exam will not cover units 8 and 9. So we spent a lot of time on unit 8, and that's why we're really focusing on units 1 through 7 here. But that's okay, because unit 8 and unit 7 are highly related. So if our time spent on unit 8 helped us with unit 7. So we just have to really focus on units 1 through 7. Okay, so we're going to start doing just mad review of units 1 through 7 starting tomorrow. We're just going to hit that review really hard because we have to know all that stuff. What I'm going to do, so I'm going to go ahead and, so first off, any questions about the exam situation here for right now?
No.
Okay, I'm going to pause the recording.